Welcome, everybody. So for those that don't remember from the beginning, my name is Nicholas Zeeb, here representing Entuitive to tell you what computational design means at our firm and basically sell you on the company. But before we begin, I want to do a little bit of exercise to wake everybody up a little bit. So here we go. I want everyone please to put your arms up like this, side by side. I see Rob doing it. That's great. Can everyone please just, all right? Cool. Great. All right, everyone keep them there. Hold, hold, hold. Okay, I want to take a quick thank you to give a quick thank you to everyone from the Toronto Dynamo user group putting together this event. It was very exciting to get everyone here. It's a great turnout, so I want everyone please, on the count of 3, I'm going to say the word clap, and we're all going to smack our hands together really loudly. 1, 2, 3. And that's all the applause you get. It's my show now. We're going to keep going. All right, so what we're going to talk about is Entuitive as a company. Then we're going to talk about what computational design means at our firm. And then we're going to talk about a new initiative that we're starting here at the company called Project Enhance, and what that means for computational design here going forward. So, Entuitive as a company. So this is our standard slide that we go and give at all of our presentations. So Entuitive is a company with over 270 plus staff. We have 7 offices, 4 in Canada, 1 in the United States, and 2 in the UK. We are primarily a structural engineering firm, but we have branched out through a variety of other services, including building envelope, restoration, special projects, and more recently in construction engineering. And then we work across a variety of sectors: commercial, healthcare, residential, transportation, you name it. And the one thing I will note as well before we jump to the next slide is that that logo there on the side, we really embody this one company culture where it doesn't matter what office you're staying at. Everyone knows each other and works across many offices. If you have a specific project that you want to work on, if you have a specific sector that you want to work in, you have that opportunity no matter where you're working in the office. I myself have worked on projects across 5 of the 7 offices despite never leaving Toronto. So that's just something I want to throw out there. It's very exciting. Okay, so a few projects that we've worked on. Anyone been to the Ripley's Aquarium just down the road? We got Rob. Anyone else? I know Rob personally. I keep calling him out. So Ripley's Aquarium was one of our first projects, and if anyone's ever been there, there's no regularity to that structure whatsoever. So at the time, it actually took quite a bit of innovations in 3-dimensional BIM to be able to get that thing built. There's about 5.7 million liters of water that had to be supported by the structure. This was a great start off to our company when we started up. The project there on the top right is the Manhattan West platform. Basically, there's this giant rail corridor through the west side of Manhattan that the city, of course, wanted to use because there's potential new building space that they could want to build over it. So we built a giant 70-meter-long post-tension slab that would support new structures above it. And while we were doing this, we had to make sure that we never interrupted the rail traffic below. So that was another really big project that we worked on that really shot the company off when we were starting. Another one that also had a problem with the rail corridor is the Central Library in Calgary. There was there's an active light rail line underneath it, and so we had to also make sure that it wasn't interrupting rail traffic. Central Library was Architect Digest's 1 in 12 most anticipated buildings in 2018, so we're really proud of that one, and we won't shut up about it. And then the last one that I want to show here is a new project coming soon, the Portland's Flood Protection Enabling Infrastructure Project, which are basically these 4 awesome-looking arch bridges. And the first one, knock on wood, will be built in May. So we're very excited about that. Okay, so computational design at Entuitive. What I'm going to do now is basically go through a few examples of past projects we've done at the firm where we've really leveraged what computational design allows beyond what typical structural engineers would be using. So I'm going to jump into this slide here, which is a bunch of logos of all the different software packages that we use at the firm. And I remember when Patrick came to me and said we really wanted you to present at this Toronto Dynamo user group, I said, well, Patrick, I probably won't mention a lot about Dynamo when I do this presentation. And he said, that's fine. We want to show what parametric modeling might be across a variety of software packages. So we're really going to focus on 2 software packages there, Rhino and Grasshopper, and we're also going to touch on a little bit of Dynamo as well. Ultimately, the reason why I'm showing all these, though, is that what you really want to be able to do is have a method to communicate between all softwares. And once you have that, what parametric modeling potentially allows you to do is run, increasing numbers of variations of the same type of structure to test different options relatively quickly. And if you take that one step further, you can also get into optimization. I'm fairly confident that there's probably most of you here will understand what evolutionary algorithms might exist in the grasshopper and rhino environment, but in case for some of you don't, I'm going to show you a little bit of an example here on what evolutionary solvers can do in these algorithms. And the solution that we're going to try and solve, or the problem we're going to try and solve today, is where is the highest peak on that surface. Anyone and their grandmother is going to be able to tell you that it's right there, but most problems aren't clear-cut like this. So we'll get into an example later about something a little more complicated and how these same algorithms can be used on a more complicated problem. So hopefully this runs. Yay. OK. So basically this little script that we've developed, we have two little sliders that can go left and right, and they move this point along this bumpy surface, and the thing that changes is the height of the point along the surface. What's going into Galapagos, which is that green component there, is the actual height of that point. And we want to try and optimize this script so that it finds the highest point on that surface. So what Galapagos is now doing is basically testing the solution space, testing a bunch of different iterations of the same of that problem to get an idea for what the problem space actually looks like. So at the beginning, it's got no idea where the tallest point is. But then as you see, as it keeps going, it starts to hone in on what the optimal solution is based on a variety of evolutionary algorithms, basically a lot of complicated math that's happening in the background. And as you see, it's slowly starting to find the highest peak is over there. And it stopped going anywhere around the structure, or the surface. So that's how the algorithms work in a nutshell. But again, anyone and their mom can tell you where the peak was on that surface, but not all problems are clear-cut that way. So to show you an example of what I might mean by that, we had one project where, for St. Mike's Hospital, where it was originally pitched to us. They wanted to take the atrium of what we were working on and create almost a cathedral-like opening so that we wouldn't have any middle columns down the center of this atrium. And it would have to support that building on top. I don't know if you remembered from a few slides ago, but cathedral engineering was not something that we specialize in. So that was something that we were going to have to try and cross that bridge. However, with the power of computational design and our structural engineering background, we can test a bunch of different options to find what might be the best one. So we have here this atrium, and if we turn on this component here, we can see there's our cathedral-looking thing. We turn off a bunch of other stuff, and we can show here now with a bunch of sliders and these viewports, we can see that as we change things, the structure changes in real time. So we can test potentially a bunch of different variations of the same structure relatively quickly. And then when we open up a finite element modeling algorithm, we can see based on the color codings which members are struggling in this model. Then when we bring out the same sort of optimization algorithm that we were working with before, Galapagos goes run, and then it takes all those sliders that we just moved before, and it tests a bunch of different iterations of the same sort of model to hone in on what it believes the best solution will be. This takes quite a bit of time, so we're not going to show you the end. We'll just show you where we got to at the final iteration. We turn that on, and this was the structure that Galapagos said was the most optimal one based on the criteria that we gave it. So as you can see, where does it go? There it goes. So, a surface is easy to figure out where the peak is, but the exact best orientation of a bunch of different beams in three-dimensional space to create a cathedral structure to optimize the lowest mass, not as clear-cut. So that's an example of how we can use optimization to further our design. But another way that we realize that we can use these parametric softwares is increasingly we're dealing with very, very modern-looking structures that really push what both structural engineering can do as well as architecture. So we got onto the Portland's Bridge project, which we talked about earlier, and we were provided with a set of models of these arch bridges that are basically going to be one continuous steel plate. And trying to model something like that just in a structural analysis software would be mind-numbingly tedious, and so we decided to not go the typical route. So instead, we went through Rhino and Grasshopper and used a variety of components to try and bring all of that information directly into our structural analysis software. And then an example of this is that right here. So what we basically used is a variety of different plugins to mesh the structure, which, again, would have been really frustrating to do that by hand. And then with a few components and a few clicks, we can bring that into our structural analysis software to start testing the design. And then further, because these bridges are so unique, there's certain things that we're really not 100% sure if we have the optimal design when we start. So for example, we have this cantilevered deck that's going to sit on the side of the bridge where people are going to be allowed to walk. when we think of the harmonics of a bridge like this, when we think of just even straight structural capacity, we don't know the exact number of spacings of webs that we're going to need. We don't know how deep it's supposed to be. All that stuff needs to be tested. In typical structural engineering fashion, there'd only be a few kicks in the can to get this right. But with some of these softwares that we're able to use, we can quickly iterate and test a variety of different iterations of the same design, changing the depth of the fins, changing the number of different fins, changing the material type and the thickness of all the materials, go from A to B to C, and quickly test a bunch of different variations to get the answer very, very quickly. So I lied a little bit at the beginning. That was one example. Now we're going to go and show an example of a project that we were working on recently, where we have a Dynamo script and what we're doing there. So basically, a little bit of background. We're only showing you part of the structure because this project is apparently confidential. And basically what we're going to show is we started off with a set of points from an Excel spreadsheet, and we need to bring all those points into REVIT and classify a set of braces based on those points. So how does that all work? Hit play. Yeah, it's working. Okay, so basically, again, first part of the script brings in the start and end points from an Excel spreadsheet. All of that gets filtered through this Python script, and then we have a set of lines at the end that we can then start manipulating in Dynamo, as can be seen by that cluster there. Again, that's not the whole structure, that's just certain things that we needed. Then, to classify all this information, we wanted to get where that is in three-dimensional space. So we took the midpoint of each brace. And then we wanted to be able to classify those braces in which level they're in. So we created a script to basically put a bounding box around each level of the building. And that can be seen here. Again, this isn't the actual building itself, but this is a bounding box being used to help classify those braces. Then we go over to this next part of the script. Now, okay. And then now this part of the script finds which brace is in which bounding box to help classify it better and add information to the model. And then the next part, we have all braces sorted by its level and all levels associated with each brace. And then once we have all that information in organized lists, we can see a few seconds later, we've now able to bring that exactly into the REVIT model. Again, not all the structure, but all the information that we classified is now available in the data table for us to be able to use to help with our design. And that is our only Dynamo example today. So one of the other exciting projects that we used a lot of these softwares for was with Search Plus Space Architects, which I didn't know existed until starting this project, to build the Mars X House. And basically, I say build, design the Mars X House. NASA hosts a 3D printed habitat competition that you can put a team together and you can provide your BIM models and really sell why you think, based on the criteria of the competition, your design would be best for habitats on Mars. We won't go into the specifics of too much of the competition, but needless to say, with our first iteration of the design, we did not come in the top 3, and it was largely because of the holes in the side of our building. Holes in space are typically a bad idea. And so when we decided to go at their second round, we wanted to create a structure, well, that didn't have any holes. And what we realized was that when you're designing something on another planet, there's no code. There's nothing to tell you, you know, what's happening on Mars. So we had to read a lot of papers. And the one thing that we found out relatively quickly was that there is no atmosphere, or very little, on Mars. So it's about 0.6 kPa. And for comparison, on Earth it's about 101.3 kPa. So to make any structure that you have on Mars habitable, you would have to inflate that structure to about 100 kilopascals of internal pressure, basically making a giant concrete balloon. And for anyone that wants another level of comparison, when we're designing a very typical pedestrian walkway in structural engineering, we're thinking of 4.8 kPa. So if we're designing it for 100 kPa, it's 20 times the pressure, and concrete in tension typically doesn't perform well. So we came up with this idea, this hyperboloid, really, really Martian-looking structure. And basically the thought behind this was, if we have this pressurized concrete vessel, and we're not really able to reinforce it with steel because you can't bring steel to Mars, that was one of the criteria of the competition, we know that on Earth, an arch is a really effective way to take a distributed load of forces and bring it into the ground. So if we take an arch and we rotate it on its side, and we revolve it 360 degrees, and we basically have this hyperboloid shape that should, in theory, distribute those forces. And that created another problem, though. The forces that go to the base, those are going to be fine. The forces that go to the roof, those have to go somewhere. So we had to create these flying buttresses that we were hoping were going to bring those forces down to the ground. So we started our analysis with a donut. And needless to say, our partners were not a fan of the donut. And so we had to then come up with a way that we could optimize the donut to reduce the amount of wall space that we had. So this is an example of our optimization script, which basically tested a bunch of different variations of our donut structure with those flying buttresses to figure out what orientation of our structure would actually create the least amount of material used and still be able to withstand 100 kPa of pressure. Ultimately, though, we found out, despite the analysis, that didn't matter what the buttresses did, it actually didn't help much, and it was also not a fan favorite of anyone that we were working with. So instead, we figured out a way that we could get rid of them entirely. Again, we don't have enough time to go through the specifics, but ultimately we came through with this design, and we were very lucky to have come in first in this phase of the competition. So that's great, and it makes for pretty fantastic marketing. Okay, so that's that. Okay, we've spent now, I don't know, 20 minutes talking about some very, very specialized projects that we've done at the firm, and I think we can all agree, per the first presentation specifically, that all these specialized things are great, but really the power of all these tools is creating things that can help us work faster and help us work more efficiently. Because ultimately, there aren't a lot of clients that are willing to spend top dollar to design a hypothetical space habitat. So this is what Project Enhance is. Project Enhance is about 11 months old. And so basically what we wanted to do was do exactly that and start using this computational design thinking and applying it to everything that we do here at the company. And so why did we choose Enhance? For two reasons. Number one, Enhance has EN in it, which aligns with our marketing, so we can do that. And number two, if we look at the definition of Enhance, it says to increase or improve in value, quality, desirability, and attractiveness. There are architects in the room. I'm sure we can all agree we want to increase the desirability and attractiveness of our structures. But for us, we really wanted to increase the value and the quality of the services that we are offering to our clients. So this was our mission statement. Despite the fact that I wrote this, I can never get it right on the first go, so we'll give it a shot. Improve the quality, efficiency, and value of our processes company-wide through the use of software and driven by a team of dedicated and collaborative individuals. That's our mission statement, which basically led to the 4 goals. So we wanted to build a team of people that knew how to use these tools. We wanted to develop a set of parametric tools to improve the efficiency across our departments. We wanted to instill computational design thinking in any new initiative that we started, so that way we were starting off from a good footing. And then we also wanted to research new business opportunities with these tools. So since we started 11 months ago, we've had 7 internal tutorial sessions, which have basically taught the basics of computational design of these various software tools to the more advanced, very specific high-end components. We've taught over 45 people at the company on how to use this software. We've implemented mandatory new hire training. We've partnered with a couple of universities to try and bring this into the curriculum because we think that this is important for students to learn. And then we've developed tools for multiple departments, which I'm going to go into now. So here's an example of one of the tools that we've developed. This is a Grasshopper component that we've put together for doing our modular design. So modular buildings have quite a different orientation of all the different modules, so there's a lot of variability to any structure we get, and there's a lot of data to post-process via ETABS models. So what we do is we basically run our structural analysis models, we have that import into our component, and then we get the information that we need out in order to quickly do our designs. As an example, it specifically shows us which columns that we've been working on that need to be reinforced, just via very easy circles to say these are the problems that you have, and here are all the capacities or the utilizations of those columns. Next, we can go and get even more granular and pick a specific column that we want to look at and get all the information that the designer needs relatively quickly to give them all the information they need to actually do any additional design work. Another example of something that we've used, I mentioned earlier that we want to start any new initiatives with computational design thinking from the beginning. So fire engineering is something that we've been promoting quite a bit at the firm. And as part of fire engineering, we've launched pedestrian modeling, which allows you to basically model for evacuation purposes as well as for any pedestrian comfort. What we are finding is with a lot of these models, once you have people starting in a certain place and people going to a certain place, there are a lot of different permutations of how those data inputs need to be done. And for a very simple pedestrian model, you can do that no problem with a quick CSV file, and then you're done. But the moment you get to something like a train station, that gets increasingly more complicated. So for example, this project in particular, again, can't go into which one it is, we wanted to know that depending on what train was coming in and how long that train was, if we knew how many people were on that train, where would they sit if they wanted to go to a specific destination? What we were doing before was basically, okay, we had to think, okay, there's tons of people. We know this many want to go here. We know this many want to go here. We think they're going to be distributed around here. If they fill a car, they spill over to the other cars. It was a lot of like mental math each time. So instead, we codified that and developed a quick Python script in Grasshopper that then exported to the right CSV files, so that for any train size that we put in, and for any passenger amount that we put in, and for any set of destinations that they go, it creates this smooth curve of where people are going to sit on the train so that they're close to their destination. And this is then, similar to some of your tools that you talked about, took days of work into seconds, which definitely saved quite a bit of time. And so that is two tools that I've talked about, but now I'm going to go into quickly, researching into new advancements in the firm, or not in the firm, sorry, looking for new opportunities using these tools. And machine learning is a buzzword that everyone uses, despite most people not knowing what they're talking about. And so what we wanted to figure out was how we could use some of these tools at the firm to either automate or make us better at some of the processes that we do. Unfortunately, we also don't have a machine learning engineer at the company, so we're learning ourselves. And so we thought, okay, we know there's tons of plugins that exist to use machine learning capabilities. We know that we can also start learning this on the side and taking courses, but we need to be able to actually apply it to something. So one of the things that we did, Jiang, if you don't mind, can I grab those? So we have a few people at the firm who can solve a Rubik's Cube. And so what we wanted to do is we have those people who know how the rules behind solving a Rubik's Cube. And so we wanted to see, okay, can we actually build a Rubik's Cube in Grasshopper and Rhino, and figuring out a way to make it actually screw itself up, and then figure out a way to teach that computer to solve the cube itself using some of these plugins. The idea here is that we know that, again, some people at the firm know how to solve a Rubik's Cube, but if we can teach the computer to solve the Rubik's Cube, we know more people at the firm who know structural engineering. So once we know the basics, we can teach them, the computer, how to do structural engineering as well. And contrary to the belief of my bosses, I'm not trying to steal anyone's job, but that's just the way the world is moving. And the video doesn't work. Darn. OK. Well, basically, this was going to show it trying to solve itself. And so you'll have to wait till maybe next time. But anyway, that's our presentation. Thank you very much for coming, and we'll talk to you afterwards.